Okay, time for questions 21 to 30 then. So first question, what are the units for the rate constant k in the expression rate equals k? And then we got x squared is second order and y is first order. So, okay, let's rearrange it to find k first of all then. So rate is, k is rate divided by the concentration of x times the concentration of x squared times the concentration of y. Units of rates are moles per decimeter cubed per second, and then each of these concentrations will be moles per decimeter cubed. So there's 3 of them. So each of them moles per decimeter cubed. That one cancels with one of them, so we're left with the 2 behind. So mole per decimeter cubed times mole per decimeter cubed on the bottom. That's going to then be equivalent to seconds to the minus 1 over mole squared decimeters to the minus 6, but of course they're on the bottom. So what this would actually equate to would be, once we bring these up, we normally put the positive integers first, so that would be decimeters to the 6, moles to the minus 2, seconds to the minus 1. So which does that match up with? That would be, oh, they've done the other way, they put them here, so that would be D. Okay, 22 then, consider the equilibrium between nitrogen dinitrogen tetroxide and nitrogen dioxide. We see the reaction is endothermic in the forward sense because we've got a positive delta H. Which changes shift the position of equilibrium to the right? Increase in the temperature. Well, yes, the forward reaction is endothermic, so increase in temperature will shift it to the right. So that's correct. Decrease in the pressure. Well, we've got more molecules of gas on the right. We've got 2 molecules here, whereas we've only got 1 molecule on the left. So decrease in the pressure would shift it to the side with more molecules of gas. Oh, that was my dog just telling me that my Amazon package has arrived. So decrease in the pressure, yes, that will shift it to the side with more molecules of gas. So that will also work. The way these work, remember, if you increase the temperature, that basically always increases rate. So if at equilibrium you've got the forward and reverse reaction are going at an equal rate, if you increase the temperature, they'll both get faster, just one gets faster compared to the other, and that's why the equilibrium shifts. So the endothermic reaction will become faster than the reverse exothermic one, and that's why it shifts to the right. Decrease in the pressure, of course, will decrease the rate for both reactions. They both get slower, but one would get slower relative to the other, and that's how it actually has the effect. But we can explain it easily in terms of Le Chatelier, where he says whatever you do to the system tries to do the opposite. So if we decrease the pressure, well, the system will try to increase it again. How does it do that? It moves to the side with more molecules of gas. Adding a catalyst, well, that increases both reactions equally. So if that's equilibrium, they're both going at the same rate. With a catalyst, they'd both go faster and they'd be equally affected. So not that one. So we're looking for A, 1 and 2 only. Okay, 23 then. So what we got here is the Gibbs free energy on the y-axis and then increase in temperature on the x-axis. And we can see that delta G is positive above this value and then it becomes negative at higher temperatures. Now if you remember what delta G is, how we calculate it, delta G is delta H minus T delta S. And there's those 4 possible outcomes where sort of it could be that it's always negative. The way it would always be negative is with a negative delta H and with a positive delta S, because of course then it'll be minus a positive value, will only be making it more negative. So where it could be, as is shown here, where it can be negative, it can be positive, is where sort of the 2 would be the same. So we'd have an exothermic reaction where this is negative, and then the entropy change could also be negative. So we've got an exothermic reaction. As long as the temperature is nice and low, the reaction would be feasible because delta G would still be negative. But as T delta S increases in magnitude, then of course this would become more positive overall because it's minus the minus number and would eventually make delta G positive. We've also got the possibility that you could have delta H is positive, so an endothermic reaction, but where you've then also got a positive delta S. So this is where sort of at higher temperatures the endothermic reaction would become more feasible because you'd have your positive value, but it would be taking away a increasingly bigger positive value here, which could then eventually make it negative. And then of course the one which should never be feasible, which is where you've got delta H being positive and delta S being negative. So it's kind of the opposite of this first one here. This one would not be feasible at any temperature because you're always going to end up with a positive value for delta G. And for delta G to be feasible, then it must be negative. So looking through, we've got the standard entropy change of the reaction is negative. Okay, well, let's have a bit of a think about that. So if the standard entropy change of the reaction is negative, that kind of falls into one of these two territories. So what we've got going on there is that with this one, basically delta G would always be positive, so it can't be this one. Here's our other possibility. Well, here delta S is negative, but the entropy change is positive. So the way that this would work is that at lower temperatures, the reaction would have a negative one, and it would become increasingly. So we'd have the great graph going more in that direction if this was the case. So it can't be this one, because otherwise it would basically be always positive if this is the outcome, or in this case, well, it's going to become increasingly positive at higher temperatures, because you've got a negative value, but then it's minus, and minus becomes a plus. As temperature increases, this becomes more significant. So it can't be that one. Standard entropy change of the reaction is positive. Well, there's a couple of possible outcomes there. So there's this one here. But again, if it's positive, well, this one, it could basically never be negative. So it always have to be above the zero axis there. What about this one? Well, here we've got a positive entropy change. And then as the temperature increases, we've got a positive value for delta V, which will then cause it to become more negative. So that looks like this here is the outcome in this reaction. That explains why at a low temperature, delta H effectively wins and it's still positive, but as T increases, the magnitude of this positive d delta S part increases and then is subtracted from delta H, eventually making it negative. So this would be the one here. At higher temperatures, the reaction becomes less spontaneous. Well, it actually becomes more spontaneous because it becomes more negative, the value of delta G, so that can't be right. And then the standard entropy change of the reaction is negative. Well, for that to work, this would have to be one of these two outcomes. So we've got this one here where basically it's always feasible, so it would never be above zero. You'd always have a negative value, which is not the case. Here's the other possibility we're looking at there. So this is where sort of it would be basically, again, going in the opposite direction. So if it was this outcome, then you'd have a negative value to start with, and then it would become less feasible as the temperature increased, because this would be our other possible outcome there. So it's not that one, so it's B. Okay, 24 then. So which species produced by the successive dissociations of phosphoric acid H3PO4 are amphiprotic? Now remember, amphiprotic means it can act as a Bronsted-Lowry acid or a base. So this thing must be a proton donor as well as a proton acceptor. And we've got the pairs here. So looking at the first one, well, this one works. It has a proton, so it can act as an acid, and it could also gain a proton to become H2PO4 minus. So that's amphiprotic, but this species isn't. It can act as a base. It can accept a proton to become this. However, it has no protons, so it can't act as a Bronsted-Lowry acid itself. So it's not this one. This one, this can lose a proton to form its conjugate base here. It could also accept a proton to become H3PO4, phosphoric acid. So that is amphiprotic. This one here, it can donate a proton to become PO4 3 minus, or it can accept a proton to become this species again. So this looks like the winner because it can do both. Basically, you could kind of have these kind of intermediates here. So you could have H3PO4 in equilibrium with H plus H2PO4 minus, and then that would be in equilibrium with 2H plus HPO4 2 minus, and then that would be in equilibrium with 3H plus PO4 3 minus. So you can see here's our first species. It's amphiprotic. It can accept a proton and go in that direction where it acts as a base, or it can donate another proton and become this, so it's acting as an acid. And then here's our other one. Again, it's amphiprotic. It can lose a proton and go in that direction, or it can accept a proton and go back in this direction. So this is our answer. Here, as we discussed before, this is amphiprotic. It can lose a proton or gain one to become H3PO4, but this one can't lose a proton. And this one here, HPO4 2 minus only, well, that can lose a proton, or it can accept one. But it's the way the question is worded, in that yes, this is amphiprotic. However, it's not the only amphiprotic species present in this range of equilibrium. So this one can act as an acid only. This one can act as an acid or base. This one can act as an acid or base. And this one can only act as a base. So what it's saying is that basically that's not the only one. This is the other one that can do it as well, so it's B. Okay, on the next one then, so we got pH is sodium hydroxide is 1 times 10 to the minus 3, and then we're given the ionic product of water, Kw. So remember, concentration of H plus times the concentration of hydroxide is equal to Kw. So, because we want to find out what the hydrogen ion concentration is so we can work out the pH value. So, H plus equals Kw divided by the concentration of hydroxide. So that's 1 times 10 to the minus 14 divided by the concentration of the hydroxide, which is 1.0 times 10 to the minus 3. Okay, so when we got indices and we have one divided by another, that's sort of easy enough without the calculator, but basically the physical difference between those. So that would be 1 times, so 14 take away the 3, that would be 1 times 10 to the minus 11. And then that's the hydrogen ion concentration. Now, of course, we don't have our calculators to do the negative log to the base 10, but when you've got a fairly straightforward number, it's just 1 times 10 to the whatever. So as long as that's a 1, that's basically 1 times 10 to the minus pH. So the pH is 11. Okay. Obviously, again, if you hadn't sort of thought through that bit and sort of you weren't sure what to do, some common sense can just help you in that. Sort of sodium hydroxide is a strong alkali, so it certainly can't be pH 3 or 4. It's got to be one of these two, so at least you're down to a 50-50 chance. But that's how you want to work it through. Okay, 26 then, so let's bring this down into the frame. So which species acts as a Lewis and Bronsted-Lowry base? And let's remember the definition. So a Lewis base is an electron pair donor, and a Bronsted-Lowry base is a proton acceptor. Okay, so those are our definitions. So here we've got this kind of complex ion of aluminium. Well, if anything, that's going to be acting as a Bronsted-Lowry acid, because of course what that can do is kind of form an equilibrium where it can lose a hydrogen ion to get this, where you'd have AlH2O5, and then you'd have a hydroxide ion coordinated to it with a 2+ charge, and then you basically picked off a H+. And of course the aluminium ion is actually acting as a Lewis acid by accepting pairs of electrons from the water where they're coordinated to it. So it's not this one, because if anything it's going to act as a Bronsted-Lowry acid by being able to form an acidic solution. Here we've got BF3. Well, boron is a good Lewis acid here, because basically if you think if we had a fluoride come in, it would act as a Lewis acid by accepting a lone pair of electrons from the fluoride. So if this is your boron trifluoride, it's trigonal planar, remember, and it's got this empty p orbital with no electrons in, well then a fluoride ion can come in and offer it a pair of electrons. So if anything, it's acting as a Lewis acid. It's going to be an electron pair acceptor, and then you'd end up with the tetrafluoroborate ion. So it's not this one, because this is a Lewis acid. The ammonium ion, well of course this is a proton donor, so again this is a Bronsted-Lowry acid, because you can get, it would form ammonia by releasing hydrogen ions. So it's not that one. What about this one then? Well, you've got the hydroxide ion. Well, there's lone pairs of electrons on here, which we don't have of course on this nitrogen, because the lone pair has been used to form a coordinate bond to the hydrogen and form the ammonium ion. So we've got 2 lone pairs on the oxygen, well 3 in fact. So it can donate a lone pair of electrons. It can be an electron pair donor, and of course it can act as a ligand. It can also accept a proton and turn back into water itself. So it'll be a proton acceptor. So it'll be this one here. We've got the lone pairs required to be a Lewis base, and it can also pick up a proton to form water. So it's a Bronsted-Lowry base. Okay, on the next bit then, move that into frame. So 27, a buffer is produced by mixing 20 centimeters cubed of 0.1 molar ethanoic acid with 0.1 molar sodium hydroxide. what is the volume of sodium hydroxide required and the pH of the buffer. So remember, in a buffer, what we need is a significant amount of both acid and the conjugate base present. So what have we got first of all? So notice they're the same concentration. So if I add here, they've got add 40 centimeters cubed of sodium hydroxide to the 20 centimeters cubed of 0.1 molar. Well, basically there'll be no acid left then, because we've got double the volume. So that's going to be 0.2 moles. That will be completely deprotonated, and all we'll have will be the ethanoate ion, and we'll also have some hydroxide ions because it's in a large excess. So it's certainly not going to be this one. It would definitely be an alkaline pH, but probably I would have thought higher than 9.2 due to the hydroxide ions. This one, again, for the same reason, well, basically this one's even sort of nonsense really, because it certainly wouldn't be acidic left, because again, we've only got these species present. There is no ethanoic acid left because there's an excess of hydroxide. This is looking a bit more sensible, because now we're adding half the amount of the alkali, so half of the ethanoic acid will be deprotonated. So in this case, this will be good. We'll have a mixture of ethanoic acid and the ethanoate ion, where the sodium hydroxide has deprotonated half of it. So we've got significant amounts, 50-50 mix of the acid and its conjugate base. And we've got the same situation here. So it's between these two. Okay. So when we're looking in these ones, I would be going in this particular case here. There's a bit of a justification for that. If you sort of think of what your acid-base titration curve would look like, if you had kind of had pH up along here, then for a weak acid, you'd have it sort of increasing sort of fairly significantly to start with, and then sort of with more of a buffer region. And then, of course, you'd reach your equivalent point, and then sort of, which is where you'd reach neutralization, and then you'd start then going towards strong alkali if you kept on adding it. So this 9.2 region, well, that's probably going to be around about the equivalence point, around about here, which is not 7, because remember, it's 7 if it's a strong acid and a strong alkali. But because we've got a weak acid and a strong alkali, once we've completely neutralized it, we've actually got this basic species present with CH3COO minus. So our equivalence point would be more around about 9.2, probably in this point here. So it must be in this acidic range when we've got so like a roughly 50-50 mixture of both. We've neutralized about half of the acid, but we still got this here. So that would be in about 4.8. That would be about 9.2. And that would, I'd expect that when we've added 20 centimeters cubed of sodium hydroxide and neutralized the ethanoic acid completely, but we haven't gone into excess. So I'm going to go with D. 28, which change represents oxidation? Well, let's have a look at these. So if we sort of apply some oxidation numbers, is that in camera? Yes, it is. Then the oxygens, of course, are -2. The hydrogen is +1. So there's definitely going to be a change in oxidation state of the chlorines. Just is it oxidation or reduction? So if this is -2, that comes to -8. This brings it up to +7. So this must be +7. Because 4 times the -2 is -8. That brings it up to -7. It's neutral overall, so this must be +7. Whereas here, that would be -6. That would bring it up to -5. So the chlorine must be +5. So that's a decrease in oxidation number. So that is a reduction. So that's not right. Nitrogen to ammonia. So here the oxidation state is 0 because it's the element itself. If the hydrogens are +1, there's 3 of them. The nitrogen must be -3 because it's neutral overall. That's a decrease in oxidation. So that's a reduction. We've got dinitrogen oxide to nitrogen monoxide. So the oxygen's pretty much usually -2, -2. So okay, if that's -2 and it's neutral overall and there's 2 nitrogens, each of them must be +1. And then here it must be +2. So this is looking like our oxidation. That's the one. We could also classify it as an oxidation because the kind of ratio of oxygen to nitrogen has increased. We've gone from one oxygen being shared between 2 nitrogens to 1 oxygen with just the 1 nitrogen. So it is actually kind of, if you view it, a bit of a gain of oxygen in terms of the ratio. Just to rule out the last one, let's go for that. So this should be a decrease in oxidation number again. So if that's -2 and it's 2- overall, then this must be +4. And if the oxygen is -2, then 4 times -2 is -8. That brings it up to -6. So the sulfur is +6. So again, that's a decrease. That's a reduction. So we want to go with C. on to 29 then. So let's work this one through. So reaction takes place when a rechargeable battery is used. So this is our lead acid battery. We've got lead and we've got the acid, and then discharge it in this direction presumably, and then we can reverse it by recharging it. So which statements are correct? Hydrogen ions are reduced. Well, let's have a look at that. Here the hydrogen's in a +1 oxidation state. Then where's the hydrogen this side? It's with the water. Well, the oxygen is -2, the hydrogens are still +1. So there is no change in oxidation state of the hydrogen. So this is incorrect because there's no change. The oxidation state of metal lead changes from 0 to +2. Well, here's the metal lead. That is a 0 oxidation state because it's the element itself. Here, the sulfate is SO4 2-, which means the lead must be 2+ because of the ratio they're in. So that is correct. The lead is in a +2 oxidation state, so that one's correct. And then lead oxide is the oxidizing agent. Well, let's have a look at that. What's the oxidation state of the lead here? If the oxygen's -2, there's 2 of them, that's -4, so it must be +4. So it's going from +4 to the only species of lead over this side, which is +2, and that is a reduction. So if it's undergoing reduction, that means it is the oxidizing agent, okay? Because then this must therefore be the reducing agent because it's undergoing oxidation. That's the way it works. So that's correct. It's being reduced, therefore it acts as the oxidizing agent. It's oxidizing the lead. So that's 2 and 3 only, which would be C. Question 30 then, bring that more into view. Okay, let's give this one a try then. So we've got a voltaic cell with silver nitrate and nickel, giving silver plus nickel nitrate with this E cell value here, which is positive, showing the reaction is feasible. So if it's a voltaic cell, let's have a go at kind of constructing that. So of course we'll have our voltmeter, and then we will have our nickel, let's call that, and let's have our silver. So if we label that as the silver and label this as the nickel, and then between them we then got what looks like some silver nitrate solution. So we'll have our Ag plus ion swimming around and the nitrate, which we probably want into, well, we could have it in 2 half cells, but I suppose we just have it in this whole one. Half cells might have been better, but I'm going to go with this now. So let's start looking through the So electrons flow from the silver electrode to the nickel electrode. Well, no, electrons flow from the more reactive one. And okay, you might not sort of have an idea where nickel is, but silver is very unreactive. So the electrons are actually going to flow in this direction. And that's kind of borne out by what's going on here, because the nickel is, you can effectively think of it as displacing the silver here. And this reaction is feasible the way it's written because it's positive. So nickel must be more reactive than silver by the fact it's displacing it. So this one's nonsense because they always flow from the more reactive metal, not the less reactive one. So that's our direction of electron flow. Nickel is oxidized to nickel 2+ at the cathode, the negative electrode. So yes, the nickel is going to be forming nickel 2+, and that's where the electrons come from, because you got nickel going to nickel 2+ by losing 2 electrons, and that is an oxidation, so that is correct at the cathode, which is the negative electrode. Now if you remember panic, positive is anode, negative is cathode, but that's for an electrolytic cell, not for a voltaic cell. For a voltaic cell it's the opposite, so panic is for electrolytic cells. Remember, positive is anode, negative is cathode. So it must be the other way around. In this case, the anode is negative. So the more reactive metal is the anode, and that's negative. So this one's not right because it's not the cathode, it's the anode. That would make it correct. So that's wrong. Silver plus is reduced to silver at the anode. Well, silver plus is reduced here because the silver ions are going to go on there by accepting electrons and turn into silver atoms. So yes, the silver ions are reduced to silver in this process, but again we've got the same problem. If that's not the anode, that would be the anode is where you get reduction in an electrolytic cell. Panic is doesn't work for voltaic cells. So what we've got is this is actually the cathode. Okay, so the positive electrode is actually the cathode. So that statement is incorrect. So then Ag has a more positive standard electrode potential value than nickel. Well, yeah, so remember the way they're written is that you have your electrode potentials go where you form the ion. plus an electron, and then if you were to flip it around, then so like what you'd have in the case of nickel would be nickel 2 plus 2 electrons go into form, and nickel go into form nickel 2 plus 2 electrons. So that's how they'd be presented perhaps in the data booklet. And I imagine this would probably be a negative value, whereas this one would then be positive. And the idea is that then this is sufficiently positive that when this is flipped and then becomes sort of the other sign itself, then it remains a positive value. So yet silver is going to be lower down the reactivity series than nickel, so it is going to have a more positive standard electrode potential. Because remember, if you think back, I know you don't have the data booklet, but at the tippy top you've got lithium, and that's got a very negative electrode potential, so it doesn't like being lithium metal, likes being lithium ions. As you move down the list and you start getting things like copper and so on, you actually start getting positive standard electrode potentials, and that tells you that they actually prefer being on the left hand side. They prefer being the metal itself rather than the ion. So the fact we've got this positive value here, silver is less reactive than nickel, so it's going to have a more positive standard electrode potential. Okay, it's happier being the metal essentially. So we're going to go with D, and that's the next 10 done.